Today we start chapter 5, and this is the second major theme in calculus. We are now transitioning from derivatives, and now we are finding the areas under the curve. And we'll get to that in a minute, but before we do that, we need to set up a little bit of notation so we can talk a little more fluidly about the areas. So the first thing we want to talk about is what happens when we're adding a bunch of numbers up. So let's say we want to add up this string of numbers. I can write it out like this, but we also have a shorthand in math and how to write sums, and it's signified by this Greek letter sigma. It's a capital sigma, and this is then called a sigma notation. And it's the two tops of the sigma are parallel. The top and the bottom of the lines are parallel, and then they come in at a point there in the middle. And what we do is we run an index on this. So right down here we say I equals, and then this is going to be our first term, and this is up here we're going to put the total number of terms. So this start right down here can either be, you can start counting at 0 or you can start counting at 1. You can call your first term the 0 term, or you can call your first term the first term. So I'm going to call this 1, okay? And a lot of, I don't know, I guess it depends on the problem, what you do. But so this means that this is my first term, okay? This is my second term. This is my third term, my fourth term, my fifth term, and my sixth term. So on the top of this sigma goes how many total terms you have. So I would put a 6 up here because I've got 6 total. And then in front of the sigma right here, you're going to write a formula of sorts involving this letter I, which is the index, that I, that tells me how to get these numbers based on what term I'm on. Okay, so this is a really easy pattern. You were looking for patterns. Well, let's see. The first term, it's 1. The second term, it's 2. The third is 3. So the pattern is that the number I'm adding up is just the index that I'm on. Okay, so the way we write that in this space is we just say it's I. And this right here, it's kind of like a function that you're plugging these numbers into. Okay, so if I started plugging in these numbers, I would say, okay, the first term I'm going to plug 1 into I, and I get 1. The second term I'm going to plug 2 into I, and I'm going to get 2. The third term, okay, you get the idea. And how far do I go? Well, I go all the way up to 6. All right, now that's like the easiest series that I can probably write out. Sometimes it's easier to see how this works with a more complicated example. So let me show you another one. Say we have this addition: 1 plus 1/4, 1/9, 1/16, and 1/25. Okay, so this is going to be my first term. This is my second term, and sometimes it helps to find the pattern if you actually write these numbers out, because then you can start to see a relationship between what this is and what number I'm on. Okay, so if I want to write this in directions, would say write in sigma notation. All right, so I draw my sigma, and I'm going to start at I equals 1, and then how many terms do I have? I've got 1, 2, 3, 4, 5, so this goes up to 5. And then how do I get this term in my sum from this number here? And that pattern that you explain is what you want to write in math language. Well, what do? I take what term I'm on, I square it, and I put it under a 1. That's the pattern that I'm seeing. So 3 squared, and then I put it under a 1. 4 squared, put it under a 1. 5 squared, put it under a 1. So my formula is going to be 1 over whatever term I'm on squared. Okay, and that's in sigma notation. All right. Now, you can also have something that's already in sigma notation, and I can ask you to calculate it. Okay, so I can say calculate this sum. I equals 1 to 5 for 3 to the I. Okay, so here the formula is already created, but now I want you to write out the string of things that you're adding up. So what I do is I'm going to take I equals 1 and plug it in. So I get 3 to the 1. Then I'm going to take I equals 2 and plug it in. So I get 3 to the 2. Then I'm taking I equals 3, 3 to the 3. How do I know when to stop? When I get to this number. So I equals 4 and I equals 5. And then I crank that number out on my calculator. Turns out it's 363. Okay? All right, so try a couple of these and see how you are at seeing the patterns. Sometimes they can be tricky. Don't get discouraged. Example 5.1, answers in the back. Okay? I think this is the check problem. I think I did the ones that are written out for you, and I want you to do the check. Do the ones that I didn't do. Okay. All right, now there we have properties of these sums. Okay. Because anytime I introduce a new concept in math, we immediately say, okay, what operations can I do with them? How do they work? And how does their world respond to addition, subtraction, all that kind of stuff? Okay, so here's how these sums respond. First of all, the sum I equals 1 to n of c, where c is just a number like 5 or 20 or negative 10. This, if you want to add all this up, this is going to be n times c. Now, think about this. This makes sense. If I have a sum of, let's say I equals 1 to 5, okay, of just the number 3. Well, what does that mean? Plug in I equals 1. Well, there's nowhere to plug it in, so it's just 3. There's no I in the expression, so it's just 3. Plus, what happens when I equals 2? Oh, it's 3 again. What happens when I is 3? It's 3 again. Okay, how many times? 5. So what is this? This is how many terms there are times the 3. All right, that's what's happening here. It's how many terms are there times whatever that number was. All right, so hopefully that makes sense. That's helpful. We also, another property is that if you have c, again, c is a number, a constant, times some function of a. Okay, this is how we notate like some kind of combination of i's, some formula for that term. So I've got a number times some kind of formula. Like for example, if there was, say, a 2 times this formula here, that's the kind of situation we're talking about. The property says that I can take that number, whatever it is, and pull it out of the sum and just multiply it by at the end. So I only have to worry about the little formula in here, plugging that out. I can pull constants out in front. Much like derivatives and antiderivatives, the constants come along for the ride. Okay. Also, we want to know what happens with addition, subtraction. So say you've got some formula with i's in it, and then it's added or subtracted to another formula with i's in it. Okay, 2 little parts to your formula. Well, it turns out that you can split those up. So in essence, this sigma notation distributes through addition and subtraction. you can take the sum of the one plus or minus the sum of the second one and treat them separately. Okay, and then the last one property is that if I'm going to sum from 1 to n of something, some formula, because this is addition, and we know how addition works, you can group addition, you can add things in any order, it's commutative. You can break this sum up. You can say, well, I'm just going to sum 1 to, say, m, some other place in the list, and then add that to m plus 1 to n. And this is it for m being between 1 and n. So basically you can split the sum anywhere you want. Okay, so let's go back to one of these examples that we had, like this guy here. This guy, this is equivalent to the sum I equals 1 to, say, 2 of 3 to I plus I equals 3 to 5. I can do it in pieces like that. As long as I hit all of the I values all the way up to 5, you can split it into two sums. Okay, those are the properties. Now, these sums can get, these formulas in here, these guys, can get pretty complicated. And if this number is very large, we need some shortcuts for adding these up, because like look at this problem that we had to add up. This gets really bad really fast. If I change this 5 to a 20, you're going to be here for a long time. So we want some formulas that allow us to add up these values quickly. Okay, and here's what they are. The first formula, we'll call these summation formulas. If you have the sum I equals 1 to n of I, okay, just whatever index you're on, that was that first sum that we did. This adds up to n times n plus 1 over 2. That's what that adds up to, and it's a quick formula that you can plug in. It's the however high you're counting times one more than that divided by 2. That's what the formula says. Okay, next formula. If you are summing up I squareds, then your total is going to be n plus whatever your biggest number is times one more than that times 2n plus 1 of that all over 6. Okay, and then the third sum formula is if you're going cubed, summing up something cubed. That's going to be n squared, n plus 1 squared over 4. Now, there's some proofs and discussion of these in the book. I will leave that to your reading if you're interested in where these come from. I'm going to show you the practical use of them. These actually will show up again in Calc 2, so they're worth a little time. So, say we want to find this sum, I equals 1 to 200 of I minus 3 squared. Okay. Well, the first thing that I want to do is I want to take this little formula here and I want to break it up into components of these, which means that I need to multiply this thing out because I need to get it term by term. So let me move this here. So this is going to be the sum of I equals 1 to 200. I'm going to square this out, so I get I squared minus 6i plus 9. Okay, that's foiled out there. And now these properties say that when I have things added or subtracted together, that I can just look at one at a time. I can distribute this summation through these three terms. Not only that, but this first property says that I can take any numbers and pull them out front. So this -6 and the 9 can come out in front if I choose. So here's what this is going to look like. I equals 1 to 200 of I squared minus 6. I'm going to put that on the outside of I. Okay. And I'm going to actually choose to put the 9 inside just because there's nothing left. It's just the 9. Okay. And now what I've done is I've created for myself, that's a property that I know right here. This is a property that I know right there. And then this is actually our first property about the constants. Remember, a sum of just constants is n times the constant. So here we go. I'm going to plug in those formulas. Now instead of this first sum, I'm going to plug in this formula. Whoops, that's supposed to be a 6. Okay, minus 6 times the formula for I, which is n plus 1 over 2. Plus, this guy is just going to be my n times whatever number I've got there. Okay, and then I'm going to do a little bit of algebra. Or calculations, okay, because what is n in our problem here? N is going to be 200, right? That's what this is, your n. It's your top value. So this is going to be 200 times 201 times 401 over 6, and this is going to be 200 times 201 over 2 plus 1800. And when you crank that out on your calculator, it's a really big number. 67900. Okay? So that's the quick way to add these guys up when you're going up to a number that's as big as 200. Okay? Try one of these. Example 5.2, the check question of 5.2. It's at the end of the example. Again, answers in the back. All right, now we're going to jump to approximating area, and I'm going to use some of this sigma notation in it. For approximating area, we don't have the formulas that we learned in geometry, you know, area of a square, area of a triangle. There's no area that defines this region. We're going to find the area under this curve. Between the values of a and b, and a and b can be anything. So this is kind of an odd shape, and because it's a curve on top, like it's almost a trapezoid but not quite because it's kind of curvy, and so there's no formulas for this. So this is the problem that we solve in the second half of calculus. The first thing that we do, we always start with approximations. So this is how we're going to approximate the area, and then we'll talk about how we adjust our approximation to make it exact. So the first method is by taking this section between A and B and dividing it up into rectangles. Because we know how to find the area of a rectangle, I can say, let's see, let me take a rectangle, and what I'm going to do is put the left hand side of the rectangle on the function. So see how that left corner is touching the function? That's going to be my first rectangle. Then I'm going to take another rectangle and make the left side touch the function. Okay, and then the third rectangle, and keep going like this. Now, as you can see, I'm missing a little bit of the area when I do this. I'm underestimating. And that's okay, we're aware of that. We're just working on, okay, how can we approximate this? And that's a decent approximation, Okay, this is what we would call finding the area with the left endpoints. So let's write a formula for this. We are finding the area of the, let me not use area twice, of the section under the curve. Okay, and we're using left endpoints. Now let's talk about how to find these areas. It's just the area of a rectangle. So I'm going to take this width right here. Okay, anytime we take a width of something, we often call it dx or delta x, depending on where you are. So this is, we call this delta x. That triangle means delta. Notation is used a lot in physics. It signifies the change in x, or that little distance. In math, sometimes we call this dx. You've seen that before. That's the distance, the change in x there. Okay. For the area, we're going to call it delta x for now in this notation. We'll change later. So, and these widths are all the same. All these widths are delta x. Okay. And when you're on an actual problem, you'll be able to count that width. You'll be able to measure it and get a number, right? And then the way we find the area of a rectangle is we go base times height. So the area is going to be the base, which is the delta x, times the height. Now let's talk about how to find the height. The height of this first rectangle right here is the height of the function at a. So I take the value, the x value of a, and figure out what is the function value at a. And in my picture, it would be 2. But the way we write that generically is, so this is specific. That's a specific height for this problem. But the way that we write that generically is we say it's delta x times the function evaluated at that first point, which is a. Okay. Now, to even more generalize it, because sometimes it's not a, sometimes it's different letters, what we're going to do is we're going to call this is going to be called x naught. That's my first x value, my starting x value. Remember, we've talked about that sub-zero means the first or the starting. Okay, so that means that this line right here is going to be x sub 1. This line here is going to be x sub 2. This is going to be x sub 3, all the way up to, and then however many you have, we're going to call this last one x sub n. Because you know, depending on the problem, you could have 27 rectangles under there, or you could have 4 rectangles under there. So we're kind of trying to generalize this idea. So we would say that the area is going to be delta x times f of x naught. That's that first rectangle. Now, what about the second rectangle? So this is our first rectangle. Our second rectangle, the area is going to be delta x again, that's the base, times, but now the height of the rectangle right here is the value at x sub 1. So we would call this times f of x sub 1. That would be this rectangle. The third rectangle, the area is going to be delta x is the width again right here. Now what's the height of this guy? Well, it's the value at this place right there. And that value right there we called x sub 2. So you start getting the pattern. Okay, that's the idea all the way up to how far do we go? Well, let's look at the last rectangle. So this is going to be our last rectangle. The width is delta x. What's the height? The height is the height at this guy. If this endpoint right here is called x sub n, then what are we going to call this right here? Think. it would be x sub n minus 1, 1 less than the end. Okay, so the area for the last rectangle is going to be delta x f of x to the n minus 1. All right, now, why did we go through all of this sigma notation? It's because what we're developing here, what are we going to do with all these rectangles? We're going to take all these areas and we're going to add them up. Okay, so our formula ends up being, we're going to sum from I equals, where are we going from? We're going from the first one, okay, all the way up to the last one. Now I is going to start at 1, okay, and go up to n. So how are we going to index this so that this works? It's going to be the width, so they all have a delta x, and then f of something. Well, the first one needs to be a 0, and the last one needs to be an n minus 1. So if you think about that for a second, okay, if I'm going to first plug in I equals 1, how do I make that into a 0? Because the first one needs to be f of x sub 0. Well, 0 is 1 less than 1. So maybe I'm going to take this and I'm going to minus 1 from it. Let's see if that works here. If my last one's supposed to be n minus 1 and I plug in n at the end, yeah, that's going to be n minus 1. So I'm kind of almost like guessing at that index and then plugging in my 1 and n and see if it works with my what I think it should be down here. Okay, so it turns out that this is the formula for finding the area under the curve using left endpoints right here. Okay, you add up all the rectangles of width delta x and height f of x sub I minus 1. All right, now this right here, just so you know what to grab onto, all of this stuff right here is kind of just the theory behind it. I'm not going to ask you to reconstruct that. I just want you to understand where this formula comes from right here. Okay, now let's look at a different situation. Same curve, but now instead of using those those left endpoints, now I want to use the right endpoints. Okay, so I'm going to draw a rectangle, same width, but instead of making the left endpoint hit the graph, I'm making the right endpoint of this rectangle hit the graph. Okay, so again, this is still going to be my x naught. Okay, this is going to be my x1. This is going to be my x2. All the way up to, this is still going to be my x sub n. So I'm still marking it the same as the red graph before. It's just that my rectangle heights are dictated by the right endpoint now. Okay, so we draw all these in. And what I want you to notice is that this is now an overestimate. Of the area under the curve. So when I'm using the right endpoints here, I'm actually overestimating. When I'm using the left endpoints, I'm underestimating the area. And that has to do with whether the graph is increasing or decreasing. That will dictate that. So let's figure out a formula for this. Finding the area of the blue region. Again, it's going to be a sum of the rectangles. So this width we're going to call delta x still. And the question is, how are we going to index it? So our first rectangle is going to be delta x times the function. And what dictates the height now? It's the right endpoint. So my first one's going to be f of x sub 1. That's going to be this first rectangle. My second rectangle is going to be dictated by the height of x sub 2 right here. okay, all the way down, and my last rectangle is going to be dictated by the height of this last guy, because that's going to dictate the height of this one. So this is going to be f of x sub n. So whereas on the red graph we stopped one short because we were using left endpoints, the blue we're going to go all the way to the end. So let's see what this is going to be of right endpoints. So we've got the sum of I equals 1 to n, and I know I've got delta x as my width. Now, how do I index? I want that index to start at 1 and end at n. So this is a little more straightforward. Well, I'm starting at 1 and ending at n. So this is just going to be x sub I. Okay, a little bit more straightforward. So this is your formula for the area of the area under the curve using right endpoints. Okay. Now, how does this work in a real life problem? In my experience, you can use these formulas. Sometimes I find it a little bit easier just to draw a really great picture. Okay, so let's do one. I've got I'm going to approximate the area under the curve f of x equals 1 over x on the interval from 1 to 2. And we're going to use n equals 4. That's a way of saying use 4 rectangles. Okay, and we're going to use right and left endpoints. So this is two problems. First do it using right endpoints, then do it using left endpoints. Okay, so let's take this guy, and I'm going to draw the picture really big so that I can see what's going on. I'm going to make 2 squares be a quarter. So this is going to be 1, 2, okay, and I'm finding the area between 1 and 2. That's what this is saying. And I'm going to just plug in some points here. At 1, when x is 1, I get 1. So this is my point, okay, on the graph. I'm trying to graph it, okay. When f is 1 1/4, which is 5/4, I get 1 over 5/4, which is 4/5. Okay, so a little bit less there. Okay, at 2, I'm at a half. So it's kind of generally coming down like this. That's kind of what this curve is looking like. Okay, if you remember this from pre-calculus, it's a swooshy thing. It's one of these guys. We're just zooming in on this little piece between 1 and 2. Okay, all right, let me, I'm going to copy this picture for our, for the next part of this, so we don't have to draw it twice. Right. Okay, first part, we're going to do right endpoints. So I'm going to start at 1 and sorry, I moved this grid off there. Okay, we're going to start at 1 and we're using right endpoints, drawing our rectangles. And the reason that I picked this scale, a quarter, is because it dictated I needed 4 rectangles. Okay, so what I'm doing is I'm taking this distance right here and I'm dividing it up into 4 sections. That's why I picked my scale to be a quarter. If I had said use 3 rectangles, I would have picked my scale to be a third for each rectangle. So just something so you can see clearly what's going on. And I'm going to label these. This right here is 5/4. This is going to be 3/2. This is going to be 7/4 and 2. I'm just counting by fourths and making them all in proper fractions. So I want to find the area under this curve. So what I'm going to do is I'm going to just add up the areas of these rectangles. So the first area, the first rectangle right here, is going to have a width of 1/4. That's our delta x, that's the width of the rectangle. And the height is going to be the function evaluated at which of these numbers, 1 or 5/4. Well, here's where it touches the graph right there, and that's my 5/4 value. Okay, so this is going to be 1/4 times 1/5/4, because the function, remember, is 1/x. So I'm taking this 5/4 and plugging it in right here for x. Now I'm showing you all the gross details. You can do this in your head. Okay, times 4/5, the 4's cancel, and you get 1/5 for that first area. That's the area of the first rectangle. Okay. Then you're going to take your next area. It's going to be 1/4 times the function evaluated at, okay, let's look at this rectangle. The thing that dictates its height is this value right here, so f of 3/2. So this is going to be 1/4 times 1/3/2. That flips over, you get the idea. Okay, you're doing this for all the rectangles, which is going to be 1/6, I think. Okay. And then you're going to do that for this at 7/4 and this one at 2. I would encourage you to finish that up. Here's what it's going to look like at the end. You're going to get 1/4 times 5/4, or excuse me, times 4/5, flip it over. 4/5 plus, this is the total area, plus 1/4 times 2/3 plus 1/4 times 4/7 plus 1/4 times 1/2. And when you do that out, you get 0.6345. That's going to be your final area under that curve. Okay, so that's how you do the right endpoints. Now we're going to come down here and do the same problem, only we're going to use left endpoints. So now I'm starting at 1. I'm off center again, hold on. There we go. I'm starting here at 1, and I'm using left endpoints. So this is going to be an overestimate. The other one was an underestimate. So let's label our values again. This is 5/4, this is 3/2, 7/4, and 2. Okay, so my area of my first triangle, again, I'll just kind of go through one of these or two of these, is right here. It's dictated, well, its width is 1/4, but it's dictated now by the left endpoint. That's what touches. So this is the value now that we're plugging into the function. The function, again, is 1/x. So this is going to be 1/1, okay, which is going to be 1/4. That's our first rectangle. Our second rectangle is 1/4 width. And now here we're plugging in this value for our second rectangle, which is 5/4. Okay, which is going to be 1/5. Okay, and then this rectangle we're plugging in 3/2, and this rectangle we're plugging in 7/4. So on this picture, the 2 doesn't get plugged in. It never dictates a height, it's just the first 4 numbers. So here's what you get in all its glory. You get 1/4 times 1 plus 1/4 times 4/5 plus 1/4 times 2/3 plus 1/4 times 4/7. All right, and some of you are saying, do I have to write the 1/4 every time, or can I factor out the 1/4? You absolutely can factor out the 1/4. Remember our properties of sums. Let me scroll back up here really quickly. if you have a constant term in a sum, you can pull it out front. Remember that property? Well, delta x is a constant term. It's just a width. In our situation, it's a quarter. So you can pull that out front, factor it out, and multiply it at the end of your sum. So that follows well. And we get here, I think the number is 7595 when you get this. Now look at it. This number 7595, that is bigger than my red area, which is 63445, which is correct because the blue is an overestimate, the red's an underestimate. So, you know, you kind of check some of those things along the way and make sure your answers are making sense. Okay, now the deal is that there's more than one way to dictate the height of the rectangle. If you go into some other calculus books, they'll talk about, hey, why don't we now, instead of using the left or the right endpoint, why don't we use the midpoint, okay, to dictate the height, like this. And it turns out that's actually a better way to do it because the midpoint of the rectangle kind of splits the difference. It's a little under and a little overestimate, and so it becomes a better estimate that way. You can use whatever for your markers for the height of the rectangle. And so we kind of come up with this general formula, and this is called a Riemann sum. Riemann was one of the guys that developed calculus back in the day, so he won the name for this situation that he investigated. It's going to be f of x sub I star, okay, delta x. Now this is, let me define that notation. For any, this x sub I star is a generic marker, so this is for, let me write it this way, sorry, better English, for x sub I star being any point in this generic interval. So this is a generic interval depending on, you know, where you are, the first, second, third rectangle. And this x sub I star is any place in here. It could be a left endpoint, a right endpoint, it could be a midpoint, it could be a third of the way through. The Riemann sum just doesn't care. It's like you can use any of those, just add them up and multiply by the width. That's the idea, okay? Now, some of you might be bothered because, wait a minute, these are estimates. We don't like that in math. We want exact values. So here's the idea. It's the same. It's pretty cool. It's kind of the same as the derivative where remember we looked at the secant line and then we took that secant line and started making it the points closer and closer together. Well, we do the same thing with this area. Here's my rectangles, right? Say I'm using left endpoints and I want to find this area. Well, look what happens. If I take these rectangles and instead of doing that, let's now cut them in half. Look what happens to my estimate. If you can kind of see the negative space, the space that doesn't get counted, like this area in here. When I split these rectangles in half, that area that's not getting counted decreases because these smaller rectangles actually pick up a lot of that missed area. And now I'm only missing a little bit in these little corners right here. Okay, and so, well, if that's not good enough, then let's make the rectangles even smaller. See what I'm doing? It's just like da, 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 da. And I can make these rectangles as small as I want. And what is happening here is that this width is getting smaller. This little delta x here is getting smaller and smaller and smaller, which might remind you of the idea of a limit, and you would be right. So what we're going to do is we're going to take this sum and we're going to run a limit. Another way of saying that these rectangles are getting smaller is saying that the number of rectangles is increasing, right? And it's increasing without bound. So that means that we take our Riemann sum from up here and we say the real area under the curve is the limit as n goes to infinity, as the number of rectangles gets infinitely large of the area. See that? So the Riemann sum is just the adding of the rectangles, but then what we find is that the area is the limit as n gets very, very large, which is why we started with these summations.